Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Andy Nightingale of Arteris. Going to talk today about optimizing data movement in SoCs and in advanced packages. Andy, we've got a lot more data coming into these devices than we've ever had before. We've got more sensors, we've got AI, which produces a lot of data. What can be done in order to improve that? What are you seeing in terms of the trends here that have to be addressed?
Yeah. I mean, obviously, it's a very big topic, and we can see that as AI and machine learning workloads continue to scale up, we need faster, low latency on-chip communication. We'll talk a second, I guess, about chiplets as well. That comes into the communication, bracket. This has really become more essential recently because of the demand for AI-powered automotive systems. That's accelerating the adoption of SoCs in advanced driver assistance systems. The expansion of edge AI and IoT applications is driving the need for lower power, higher performance architectures. All of these systems have huge amounts of data these days going across hundreds of IP blocks, and the demand for, as I say, performance is going up. The requirement for latency in real time is coming down, and everything's getting more complex. But the problem is that the more complexity, the more blocks, and the more wires that you have to connect everything up together.
So, what does this look like in the market? What are you actually seeing going on out there? Because you're obviously touching a lot of different pieces of this.
Yeah, let me show you. The system on chip market continues to grow, and it's got a strong growth trajectory. It's projected to expand from around 139 billion in 24 to around 206 billion by 2029. So this is really reflecting a compound annual growth rate of around 8%. As we're looking on these slides here, the accelerating complexity really covers the movement of data across designs of multiple topologies in different applications. And we've got the rise, obviously, of artificial intelligence. By 2030, the total generative AI compute will serve 70% of business to consumers and 30% of business to business applications. We've got AI going across the board in terms of automotive as well. So, for example, the demand for AI-powered automotive safety systems is accelerating the adoption of SoCs in advanced driver assistance systems. We've got the expansion of edge AI, IoT applications. This is driving the need for low power, high performance NoC architectures. And of course, we've got the rise of chiplet technology with multi-die systems that are now going beyond Moore's law, that we have to obviously cater for the interconnectivity between the chiplets themselves.
You've got a lot of pieces here, and the number of pieces that you have is actually increasing. That makes moving the data that much more complicated, right?
Oh, absolutely. Let me show you another slide. So as we can see here from these charts, that this surge in SOC complexity is pretty clear, and it's primarily driven by the increasing number of IP blocks. And we see SoCs being designed today that they're integrating over 300 IP blocks, most of which require minimum latency, high bandwidth communication between them. And the main reason for this is that the type of connectivity is essential for real-time decision making. And legacy network on chip architectures are struggling to keep up, basically. It's creating bottlenecks, and it delays product launches and drives up engineering costs. And to remain competitive, companies must shift towards smart, scalable, and AI-driven NOC solutions that enhance the integration efforts of all these blocks, optimize the performance of them, and really accelerate the company's time to market.
This is all about moving data over wires, and you've got more wires that you have to now connect. So the idea here is to make them as short as possible in order to reduce the latency, but also reduce the power, right?
Right. So as we have more IP blocks, we mentioned, 300 or so IP blocks connecting together. There's a wide data width requirement as well as we get more data and more complex data coming through. So the number of wires themselves are effectively increasing, and that's really pushing up the SoC power consumption itself as a whole.
So how do you deal with this? Because you have a lot of pieces here. I mean, you've got potentially multiple knocks per device, right?
Oh, absolutely. Yeah, let me show you another slide. So we've established that SoC designs today demand this cutting edge network on chip technology that simplifies SoC designs and reduces the number of wires in the design. Just stepping back a second to actually look at the overall SoC view and the interconnectivity there of all these wires. So with 5 to 20 NOCs per chip or chiplet, these interconnects account for about 10 to 13% of the silicon area. Registers themselves, they consume about 3 to 20%. So this makes efficient interconnect designs a critical factor for modern stocks. So IP is needed really to enhance integration, functional safety, power efficiency, performance, die area, and also time to market. So this really needs to reduce all of these design bottlenecks, the IP that they use.
And this gets layered too, right? Because you not only have to deal with the connections, you also have to deal with things like timing. How do signals get from one side to another in the proper time slot so that you're not sitting there waiting for something else to move through?
Yeah, that's right. You've got not only the performance of the data, but the management of the quality of service throughout the network. You've got pipelining as well as you transport signals across the chip in multiple cycles. So there's a lot of coordination and complexity going on as well. And that's all part of the knock. And that all contributes to, again, increase wire count or increase wire length overall.
How about things like signal integrity? How does that fit in here?
Yeah, so we've got to be obviously careful with signal integrity again, because the number of wires that you have and the closer they get together as they're routed does affect, capacitance, signal integrity in the overall design. So again, what we want to do is minimize congestion. We have really the need to have a smart way of identifying congestion and hotspots in that respect to actually give as much space between the routing of the wires as possible, and to actually reduce these congestion points, if you like, on the floor plan where routing gets very tight and you get these signal integrity errors potentially coming up when you get to the physical part of the design.
So Knox have been around for years. As a matter of fact, companies have developed them themselves. What's changing here? How do we make them more efficient? How do we make them easier to create? And also, how do we deal with all this exponential increase in complexity and just about everything else?
Absolutely. So really what you need is a knock expert in the room alongside you. And what we mean by that is the introduction of something called a smart network on chip that really addresses all the problems of routing around floor plans, making sure the quality of service, the latency, the performance is all up there. So what one needs, again, is an expert in a box that comes along and helps you design the optimum network on chip. And this is, again, what we call a smart network on chip.
And really, what you're saying is that this has to integrate a lot more tightly than it did in the past, right? With much more complexity.
Absolutely. You have to have IP that's aware of physical constraints, IP that's aware of physical constraints like the floor plan itself, and potential signal integrity issues. And we're really doing a shift left here, and actually anticipating problems that might be coming up in the physical design and actually solving those right up the front end. And all those smarts really need to go in the design IP in order to create a network on chip interconnect that doesn't have to keep coming back from the layout team for adjustments and modifications. That's very time consuming, very expensive.
So, how do you optimize it? What do you do next?
Okay, so let me show you something about the smart knock technology that we have. So really, a smart network on chip is an advanced interconnect solution designed to manage the increasing complexity of these modern SoCs. So unlike traditional NoCs that are basically manually driven, a smart NoC automates the design process. It really significantly reduces the manual effort that a designer has to put into getting the optimal network on chip interconnect out.
So why did it take so long to actually get to this? We've been talking about Knox for years. I mean, what's changed here?
So what's really changed is that with the advent of artificial intelligence algorithms that we've been developing literally over the last few years, we're actually now being able to capture the knowledge of expert designers and, as I mentioned, actually put that expertise in the box and actually apply that and identify that and recognize, challenges and constraints and actually work around them so that the designer doesn't have to manually work that out and work through that, or worst case, realize that they've made that error in judgment, should we say, when it's too late. When the physical team are actually working on the layout, and the design has to be reworked as a result of correcting some of these decisions that were made earlier on.
So if I'm a designer, what do I actually have to do here?
Yeah, so as we've started to show the process here, the smart knock flow really has four main stages. So in the first instance, a designer defines the interfaces of the IPs that they're integrating. Remember, we said we had up to about 300 in any one given knock, and they define the connectivity of these interfaces. They also enter a floor plan. Now, this can just be a bitmap or a Visio file, or actually even a screen capture from a whiteboard. They then enter the knock objectives, as we call them, which really amount to the performance targets of the design itself. How quick we want data to come across, what priorities for certain datas that we should assign, what's more important, what's less important. And then the smart knock comes into play to combine these inputs and requirements to create the knock architecture itself. And finally, this generated knock IP is then output at RTL and physical synthesis scripts to go off to the layout team. Now, the crucial thing here is that in this third stage, the designer can actually step in and actually interact with the smart knock if they want to change stuff. And this is really groundbreaking stuff. It's not a respin if you don't like it. It's actually a let the smart knock work. And if you want to change something, make changes, and it then carries on with those changes in place as well. So this is really is like having a smart designer in the room with you, because you can pause them, you can make some changes, they can accept that, and you can actually carry on with those changes embedded.
And that's important both for the traditional ECOs that come into an SoC, but it's also important now as we get into chiplets and more choices that you have of where are we going with this? What can we do? How do we optimize it? We have multiple choices for chiplets, and that's only going to grow over time. We have multiple ways to connect them. This becomes a way of saying, okay, here's the what happens when you do it this way, right?
Yeah, so at the moment, what we do with the smart knock is we're really focused on the individual knocks themselves. But of course, we know what the requirements are on the boundaries. So you can basically take one set of requirements from one knock or subsystem or chiplet, if you like, and actually start from that point on the other part of the chip with a new knock and a new set of requirements. And then the physical, the die-to-die interconnectivity, that's actually handled just through, from the NOx perspective, from a standard interface, but then has a physical pipe, if you like, that actually connects the two together. But what we're doing here again is we're using the smart knock to design, if you like, the knock on the left-hand side and then the knock on the right-hand side. But because you're defining the constraints there, because you're telling, what the objectives are at either end, you can actually make up a pretty powerful system of sub knocks or little chiplets, if you like, on the die itself.
How does this work in the real world?
Yeah, let me show you. So Greenchip, a leading automotive semiconductor company, used FlexGen to develop a high-performance ADAS SoC. This is an advanced driver assistance system. So they needed to address the challenges of integrating an AI-driven vision processing system with multiple IP blocks. So this really made a great case study, as our previous discussion, for use of a smart knock. And their design required stringent latency and bandwidth optimizations as they were going for real-time sensor fusion, as well as having to meet the strict automotive safety standards, of course, as well.
And you mentioned sensor fusion. You have a lot of sensors that are in a car these days. All that data has to come together and you have to make sense of it in real time, right?
Oh, absolutely. Yeah. I mean, in terms of the latency and bandwidth and performance, we're really looking at the lowest possible latency for real-time operation here. And that really we encode into the requirements when we talk to the smart knock and we set it up and we actually give it what we call the traffic class, or really identify or tag which parts of the data flow are real time, and therefore which parts of the data flow really have to be the lowest possible latency for the best results.
So, how did this turn out? What did it actually look like in the real world?
So if we look at the key takeaway metrics from this case study, we're looking at the knock design time, and we're actually comparing from a manual process going through the design versus a smart knock IP process. So in the traditional sense, the design time for the first iteration of this was, say, 4 to 6 months. Now, when we come in with the smart knock, we're looking at a 4 to 6 weeks turnaround for knocking out the same class of design. So improvement here, we see 80% faster. We talked a lot about wire length optimization in terms of the overall system power. So from our baseline, we actually measured a smart knock generated version that was 27% smaller or shorter wire length in the design. And this really gave a latency reduction as well. When the smart knock was working on the constraints, it actually managed a 40% faster data flow. And with the wire length optimization, the latency reduction, the smart knock also managed to come up with a configuration of the knock that was 60% higher throughput overall. And then finally, on the timing optimization iterations, we took 5 to 10 iterations on the manual knock process. And then when we applied the smart knock to it, we took less than 2 iterations to actually achieve the same result with a 90% faster closure on the timing optimization.
One of the interesting things in these numbers here is that the number of switches and links actually went up when it was automated, but they were shorter, right? So you basically made it more efficient.
Yeah, what we're doing here is we're actually increasing the efficiency by looking at perhaps where the congestion points are and breaking these into more switches. So it might sound a little bit sort of contrary to logic, but it actually makes sense if you think about fewer switches having far more wires and therefore more congestion and more density around them. If you actually split the design up and actually spread the switches out and actually reroute the wiring, which is very tedious, but obviously not for a machine to do. Then you get overall, as you can see here, more switches, but the overall wire length actually reduces. And again, as we saw from the results, the SOC power comes down by 27%, as we said. We get faster data flow, higher throughput. So very pleased with these results.
So, given all this complexity, we're way beyond what a person can keep in their brain, right? They need
Mm.
some sort of equipment now in order to be able to do this, some sort of tools. And those tools have to become more granular as these things become much more complicated as well, right?
Oh, absolutely. Yeah. I mean, in terms of the tooling, that's all built into the IP itself. But simply put, FlexGen really revolutionizes the knot creation. It really significantly accelerates the development cycles. It optimizes the overall wire length that we've seen. It contributes directly to SOC power efficiency. So design cycles that took days or weeks can now be completed literally within an hour. And as we said, FlexGen is like having an expert knock designer in the room, so that engineers can reduce, the front end development time by 80%, so achieve faster prototyping, or, and this is the important point, I think, is actually spend the time saved doing more of their own IP innovation.
Andy Nightingale, thanks for a really interesting insight into what's going on here.
My pleasure, Ed.